Okay, so recalling here the first principle of thermodynamics, we had that Q minus W equal to the change in energy. Okay, so for any type of cycle, okay, I'm just going to do this one here. It doesn't matter which way it is. So let's just say that we start from one pressure, 1, 2, 3, 4. Let's say you go clockwise, okay? But here what's important is that you start one point and you end up to the same point. So that means that the change in kinetic energy, final velocity is equal to initial velocity, the change in potential energy, change in height, same height, and the change in internal energy at the end and the beginning is the same, so it's 0. So that means that all this term here is equal to 0. So the first principle of thermodynamics gives that you can transform all the heat into work, or vice versa, you can transform all the heat into work. So basically the equal sign here implies that this process here is 100% efficient, okay? However, we know that in real life, that cannot happen, all right? So what happens in real life, and this is the important part, is that if you have a system over here, that system will always be operating. So you will have here, let's say, a hot reservoir that will provide heat to the system. Think about your steam machine. And now your steam machine will produce, let's say, work. So in that case, this equation is valid. You can transform all the heat into work. But what happens? In real life, every engine, if this was the absolute 0, this would be true. But every time when you operate an engine, it's between two temperatures. Let's say the temperature of the engine and the ambient temperature. So that means that the system is losing heat to what is called to a cold reservoir. So really from here, what we can see is that the efficiency, the amount of work you can get really depend on the difference, how large the different temperature is between the hot and the cold reservoir, all right? So if it was 100%, the efficiency would be okay, so let's say if we want to generate power, would be whatever is the change, whatever is whatever you get out, efficiency is what you get out divided by what you get in, what you put in. All right, so what do you get out? You're trying to get work, and what you put in, you have QH. What you put in is QH, okay? All right, so now the amount of work here really will be equivalent to QH minus Q cold, which is the amount of power you can get, divided by Q hot. And this basically gives you that the efficiency in this case is equal to 1 minus QC over QH. So this is actually the efficiency for a power cycle, okay? So this would be, since this is generating work, this is a power cycle. So the efficiency for the power cycle that is known by the letter eta here, and that's equal to 1 minus QC over QH. And here I'm just going to introduce something that we'll see in a later chapter, but let's say the temperature of the cold reservoir is TC, and the temperature of the reservoir of the hot reservoir is TH. This is equal to 1 minus Tc over Th. So basically, this is the efficiency of a power cycle. All right. If you want, I'm going to add one more thing. This is really for an ideal. This is the ideal case. All right. Now, let's say that instead of a power cycle, we want to have a refrigeration cycle. So what is a refrigeration cycle? This time you need to put cold inside the system. In order to do that, what's going to happen? Instead of create power, you need to add work or power into the system. So let's come over here. And let's see what happened for a refrigeration cycle. So the refrigeration cycle, again, we have here our system. So this time, this is what will happen. We'll go from the cold and obviously in order to go from low temperature to high temperature, you need to put work or power into the system. Okay, so really here the refrigeration cycle is when you look at this section right here. All right. In that case, what is it? The efficiency the textbook used the letter beta is whatever you get out divided by whatever you put in. Yes. So what are you trying to get out over here? You're trying to get out what? Q of C. This is what you're trying to do, put cold into the system. That's why it's called a refrigeration cycle. And what you need to put in, you need to put the work or power. And this would be equal to Q sub C. Again, the amount of work that can be provided is proportional to the change in temperature or the heat between the hot and the cold reservoir. And basically you end up with a relation beta equal to QC QH minus Q sub C. Or if we assume that the cold reservoir is at a temperature Tc and the hot reservoir at a temperature Th, this would be proportional to T cold, T hot minus Tc. Okay, so this part will be important for the next chapter actually. All right. So now we did the power cycle, refrigeration cycle, and the third option now is what would be called a heat pump cycle. So you try to remove the heat from the system. So heat pump same figure as before, hot, T hot, needs to come out. This is our system. Okay, we remove heat from the cold reservoir at a temperature Tc. So it's exactly the same figure as before, but this time the section we're looking at is this one over here. Okay, we're removing heat. This is the heat pump. Then the heat pump, we're gonna have the efficiency, which your textbook uses the letter gamma. Again, it's equal to whatever you get out, and you divide it by whatever you put in. All right, so what are you trying to get out over here? You're trying to get out the heat. Q hot, what do you put in? The work, so you're gonna have Q hot divided by Q hot minus Q cold. So if we do the same thing as before, this will give you that the efficiency of the heat pump is Q hot divided by Q hot minus Q cold, or this would be equal to T hot minus T cold. Okay. Okay, so here the only thing is that you need to be careful is that in here for the power, this coefficient here is always lower than 1, okay? But in this case, for this one over here, the beta will be higher than 0, many times higher than 1, okay? So generally for the refrigeration, I think you will have coefficients between 3 and 5, all right? And for the one of the heat pump, it's about the same situation. So let's we have this page, this one, and this one over here. All right, so let's try to do some examples. All right, so let me go to the textbook. Okay, so an example, I went to the textbook and let's do 287. We'll do that one later. Oops. So let's see, 287 is this one over here. So they say, as shown in figure 287, a cogeneration power plant operating in a thermodynamic cycle at steady state. The plant provides electricity to a community at a rate of 80 megawatts. The energy discharged from the power plant by heat transfer is denoted on the figure by Q out. All right, so basically just copy this figure of these 70 megawatts is provided to the community for water heating, and the remainder is discharged to the environment without use. The electricity is valued at 0.8 cents per kilowatt hour. All right, the thermal efficiency is 40%, which is here. We need to determine the rate of energy added by heat transfer, Q in, okay? The rate of energy discarded to the environment in megawatts, so again, that's Q out, and the value of the electricity generated in dollars, all right? So if we do some type of the figure here, this is a power plant, so this would be a power cycle. All right, so this is, let's say, problem 287. So let's say we have here our power plant. That we know is 40% efficient. Okay? That's basically what we have from the figure. That one received Q in from probably a hot reservoir. So basically, let's say this will be Q in. All right. This is a hot reservoir. You can plot it or not. And now what else do you know? Is some power going out. So there is Q out over here. Okay. Looks like some of this Q out all right, so, and let's first go to the other one. Let's do one thing at a time. And this power plant generate 80 megawatts of electricity. So basically the electricity here, power is 80 megawatts. All right, so I know I'm missing stuff, but we do it one at a time. So let's see, what do we need to find? The rate of energy is added by heat transfer. So Q in megawatts. Okay. We need to find first part, A, Q in. All right, so what would be the efficiency of this power plant? Will be the efficiency would be whatever you get out divided by whatever you put in. What do we get out? 80 megawatts. What do we put in? Well, we need to find the Q in. So basically, we know that the efficiency, this one is 40%, which will be 0.04. Or it will be, sorry, 0.4, it's 40%. All right, so from here we can get that Q in will be equal to the amount of power generated divided by the efficiency, which is 80 megawatts divided by 0.4. Okay, so give you 80 divided by 4. So this will be 200 megawatts. All right, part B. We need to determine the energy that is discarded to the environment in megawatts. So I guess Q out will be the overall. Okay, all right. So I think here we can go back to the camera. So is this Q out on the picture? Because this is discarded to the environment, but some of it is recovered, okay? So what we need over here is to find Q out. Okay, so what do we know over here? We know that the total power that you can generate will be the difference between the hot reservoir, which is Q in, minus the cold reservoir, which is in this case is Q out. So from here, you find right away that Q out will be equal to Q Q in minus the amount of power out. Or if we do the substitution, will be equal to 200 megawatts minus the 80 megawatts over here. So this will give us that Q out is equal to 120 megawatts. Okay. So next, what do we know? So let's say out of this, $120 megawatts, 70 are recovered for water heating. All right. And do this, and then we can just say let's call this one Q heating. So H, there is 70 megawatts. Okay, so all right. So what's the question in 2? I think I know what's going on. So really question 2 was to determine discard it to the environment. Okay. All right. So really there is, let me do this a bit different. There is Q out is 120. Out of this 120, 70 megawatts are used for water heating, meaning that the left going to the environment, say Q environment, will be equal to what? Should be equal to 120 minus 70. This will be 50 megawatts. Okay, so I think that's the answer they're looking for. And part C, they ask us to find the value of the electricity generated in dollars per year, okay? And we know that the value of electricity is 8 cents per kilowatt hour. All right, so over here, basically what is the amount of money per year? So the amount of money here is basically, this is your system. You're gonna charge your customer by the amount of power generated, okay? And you know that the cost here of electricity, how much you can charge is $0.08 per megawatt hour. Let's double check, per kilowatt hour. Per kilowatt hour. All right, so we know that this one over here is equal to A. Okay, so the amount of money you're gonna make, let's say, is amount of money per year is equal to what? It's equal to the 80 megawatts times the 0.08 cents per kilowatt hour. So over here, the first thing I do is to transform the megawatt into kilowatt, and basically you know that 1 megawatt will be 1,000 kilowatts. So this will give us what? Cancel this megawatt with this megawatt. You cancel this kilowatt with this kilowatt. So now we need to have per year, so we know hours. So let's see how many hours we have in a day. So 24 hours times 365 days in 1 year. Okay, so if you do the calculation, this will give you that the power plant could generate an income per year or could charge approximately 56 millions. All right, so these problems are not difficult, but you really need to pay attention to the units. Okay? So let's do the problem that was above. I like this problem, the 286. Okay, so let's do this figure over here, and then we can read the problem. So in problem 286, let's say we had a cycle A that's connected to a cycle B. And what's happening here is that, let's say, coming from a hot reservoir, Q1, then you're gonna have between A and B, Q2, and then this is going to another reservoir here, Q3. Each one of these power cycles, this one will have an efficiency F sub A and this one F sub B, and both will generate power or work, WA plus WB. Okay, so let's read a little bit what the problem statement says. So figure 286 shows two power cycles, A and B, operating in series with the energy transfer by heat into cycle B equal in magnitude to the energy transfer to the heat from cycle A. All energy transfers are positive in the direction of the arrows. Determine an expression for the thermal efficiency of an overall cycle consisting of cycles A and B together. So it's this part. And what do we know about this one? Operating in series with the energy transfer by heat into cycle B equal in magnitude to the energy transfer by heat from cycle A. Okay, let me redo that again. Determine expression for the thermal efficiency of this one. With energy transfer by heat into cycle B equal in magnitude to the energy transfer by heat into cycle A. Okay, I don't know what is that for, but we'll figure it out. So we need to find this one for an equivalent that would be operating between Q1 and Q2. And we know that, okay, I think I know now what's going on. Okay. So basically, this is what we have. All right, so we're gonna go over here. So over here is two power cycles in series. This is one single power cycles operating between Q1 and Q3, but that will have the same amount of output power or output work, okay? So let's start at this one. Let's say we first look at the efficiency of A. So it will give us that the efficiency of A will be equal to what? Whatever you get out divided by whatever you put in, Q1, okay? So this will give, this is Q1 minus Q2 divided by Q1, which will give you 1 minus Q2 over Q1. And let's say this will be our equation I. We do exactly the same thing for the second one, all right? So that will be equal to what? Whatever you get out divided by whatever you put in, Q2. This time this will be Q2 minus Q3 over Q2 equal to 1 minus Q3 over Q2. And this will be our expression Roman 2. Okay, we need to find out what would be the efficiency of this one. The overall efficiency of this one will be AB. AB will be equal to what? Whatever you get out divided by whatever you put in, which is Q1. Now, you know that this one, WA, as we did over here, will be Q1 minus Q2 plus Q2 minus Q3 divided by Q1. And you can see right away that the Q2s will cancel out. And this is equivalent, which makes sense, just the temperature of these two, the temperature change or the change in heat between these two, Q1 minus Q3 divided by Q1, which will be equal to 1 minus Q3 over Q1. And this will be our equation 3. All right, so now if we go back to the problem statement, what do they ask us to find? They ask us to find the determinant expression for the thermal efficiency of the overall cycle, so the theta AB, okay, together in terms of the individual thermal efficiency. So what we need to find is this expression here, just in function of the efficiency A and the efficiency B. And we can see over here that this is equal to the ratio Q3 over Q1. So now the thing is that how can we get Q3 over Q1 using these two relations over here? All right. So what we're going to do, let's see, we need Q3 over Q1. So we can solve this one for Q2, this one for Q2. We equate these two equations and solve, and it should give us something in function of Q3 over Q1. All right, so let's do that. So we're going to do solving for Q2. Equations, Roman 1 and Roman 2. Okay, so let's recall what are these two equations. The first one is this one over here. So it will be A equal to 1 minus Q2 over Q1. So this one will give what? Q2 over Q1 will be equal to 1 minus efficiency, which will give you that Q2 is equal to Q1 factor of 1 minus the efficiency of A. All right. Similarly for the other one, when we have the efficiency of B, 1 minus Q3 over Q2, 1 minus Q3 over Q2, which gives Q2, which gives Q3 over Q2 equal to 1 minus eta sub B. But this time, this is going to give us that Q2 actually will be equal to what? Q3 divided by 1 minus the efficiency of B. Okay, so now we're going to equate the two expressions. So equating, what do we get? Q1, 1 minus the efficiency of A equals to Q3 divided by 1 minus the efficiency of B. And remember that what we're trying to find is the ratio Q3 over Q1, okay, on the combined one. So this is going to give us Q3 over Q1 will be equal to what? 1 minus eta sub A times 1 minus efficiency of B. All right, so finally, all we need to do is to go and substitute now this expression into this one over here. Finally, substituting into 3, what do we have? The over efficiency AB equal to 1 minus Q3 over Q1 equal to 1 minus efficiency of A times 1 minus the efficiency of B. So this should give you 1 minus, so we expand, this will give us 1 over here minus the efficiency of B. We do this one minus the efficiency of A plus the product of A and B. So you can see that the 1 would cancel out. So we get at the end that the combined efficiency of AB is equal to mu sub A, efficiency of A, plus efficiency of B, minus the efficiency of A and B. And that will be the answer. Okay, so let us back to this problem over here. The reason I like this one is because I think it has a bunch of practical applications. So imagine over here that there is hurricane season and you want to check if what is the best option for you to provide power to your house with 2 generators. Okay, generator would be a power cycle. So you consider the 2 cases. Do I need to buy 1 big generator that will create the same amount of power as the 2 little ones? Okay, operating obviously between Q1 and, oops, here I did something wrong on the figure. This should be Q3. Good, I spotted. So the same temperatures, but the only difference is that you need to find out if it's better to buy 2 or just 1 big one. Okay, so let's see what is the best option. So in general, you will find out that the efficiency of a power cycle, let's say of any generator, at the best is 30%, which will be basically 0.3. Okay, so if the efficiency of each one of them is 0.3, what should be the efficiency of your single engine? This one over here. Okay, this should be the eta AB, which we find to be equal to the efficiency of A plus the efficiency of B minus the product of the efficiencies. So you do the calculation, this will give you 0.3 plus 0.3 minus 0.3 squared. Okay? And this will give you an efficiency of approximately 0.51, which is 51%. So now, what is the conclusion? Is it possible to find a power cycle or generator with an efficiency of 51%? So obviously the answer is no, because the maximum you can get is about 30%. So meaning that it's not to see which one is better. The only option you have is to buy 2 generators in order to create a total amount of power that will be the power of A plus the power of B. So you don't have to buy 2 generators, because if you want to do it with 1, it's not feasible because you will never find a generator efficient enough. Okay? So probably the other option is what? Is to buy 1 here that will have a lot more power output, which efficiency will be 0.3, so that the overall power will be probably equivalent to this one. All right? And that's it. That's all I wanted to do really for this class. It's probably not an hour and 15 minutes, but I think we can stop it over here.